In this video, we're going to start discussing directional derivatives. In order to motivate this, I want to quickly go back and talk about partial derivatives and recall what they were able to compute. And so the partial derivatives were derived because they were able to compute the rate of change in the direction parallel to the coordinate planes. Right? So for example, if I computed the partial derivative f sub x, the partial derivative of f with respect to x, this gave me the rate of change in a direction parallel to the xz plane. And similarly, the partial derivative with respect to y gave us the rate of change parallel to the yz plane. And so we can figure out the rate of change in those two directions, and those two directions are probably the most important in a lot of physical applications. But sometimes we also want to look at other directions. So our goal here in defining directional derivatives is we want to be able to compute the rate of change in any direction, not just in the direction of one of the coordinate planes. Now to do this, we need to quantify a direction in some way. And luckily we were able to do that. We can represent a direction with a vector. All right, so we're going to use vectors to specify the direction that we want to compute the rate of change in. And to be even more specific about this, when we want to talk about a direction, we don't care about like sort of a distance or anything like that. We're just caring about that direction. So what we're going to do is we're going to focus on using a unit vector in that direction. And that way we'll always end up with the exact same value because the unit vector, in any particular direction, there will only be one unit vector. So that is what we're going to use to indicate the direction in this context. So in order to find a formula to compute this rate of change in any given direction, we're going to start by supposing we have a function of two variables. Now this could quite easily be extended to three variables, but we're going to focus on the two variable case here. All right, so we're going to suppose a couple things about this function. We're going to assume that it's differentiable, and that we're going to assume that x and y are both functions of a variable t. So we're going to say x is g of t, y is h of t. Now the functions g and h won't be that important. It's just the fact that we can write them both in terms of t. And so once we have this set up, we have the chain rule, which we can apply. And the chain rule says that the derivative of f with respect to t, this is a one variable derivative. This was our first case of the chain rule in the previous video set. So we have df dt is going to be del f del x times dx dt plus del f del y times dy dt. Okay, so this gives us the rate of change with respect to t. Okay, which is not quite what we want. We don't have a direction here. And so in order to get a direction, we want to pick a unit vector in the direction that we're interested in finding the rate of change. So I'm just going to call that u, and we'll call its components u1 and u2. Right, so now we can actually write down what we want to compute. So we're going to denote the derivative of f at a point a, b, so this is just some point in the domain of our function, in the direction of u, so in the direction of that unit vector we picked, we're going to denote this derivative by a capital D, a subscript of the unit vector u, f of ab. So this is going to be our notation for the directional derivative in the direction of u. We haven't, of course, defined it. That's what we're about to do. But just to introduce the notation so that we can use it going forward, now that we have all the pieces. So the next goal then is to define how we compute this. And so to start that, we're going to let C be a curve given by the following vector function. So we're going to define r of t equals a plus t u1 and b plus t u2. Now you should recognize the form of this vector function. This is a line. It goes through the point AB. And it has the same direction of that unit vector u that we picked just a moment ago. Right, so with this line, with this curve parameterized in this way, we can define this directional derivative to be the derivative of f with respect to t, which we computed above with the chain rule, evaluated at the point AB. So to get the curve C that we just defined involved, we're going to quickly compute the distance between the point AB and a point on the curve C given by a plus t u1, b plus t u2. And this will be a quick calculation. So the distance between them, we use the distance formula, which we know is the square root of the sum of the squares of the differences of the corresponding components. And so if I subtract the first points, the first coordinates of my point, I'm going to get tu1 squared. The a's will cancel out. When I subtract the second coordinates of my point, I get tu2 squared. Okay. And of course, I can factor out a t squared from this, and we have u1 squared plus u2 squared. Right. And this is equal to t times the square root of u1 squared plus u2 squared. But remember, that's just the magnitude of the vector u. And u is a unit vector. So the magnitude of u is just equal to 1. So the distance between the point AB and a plus tu1, b plus tu2 is simply t. Right. And so what this tells us is that this notation that we've just defined, d sub u of f of ab, is the rate of change of the function f at the point AB with respect to the distance along the line C. Because if we substitute Tn on this line from our base point AB, we're going to get a point that is t units away. So if we substitute in 4 for t, we're going to get a point that's 4 units away. And that is another way of saying that we are parameterizing in terms of the arc length parameter. Right? The parameter actually gives us the length along the curve from our base point, in this case AB. Right? And so this allows us to actually compute a formula for the directional derivative, because we know how to compute derivatives of multivariable functions. Right? So our formal definition is going to be the following. So we're going to call this, like I've said a couple times, the directional derivative. Right, so it's going to be of the function at the point in question. So of f of x at the point AB in the direction of the unit vector u. Right, so this is all just the setup that we've went through previously. And I'll give those coordinates u1, u2 is given by this formula. We're going to take the limit as t goes to 0 of the expression f of a plus t u1, b plus t u2, minus f of ab, all over t. And so this just puts everything we've just done back into context. We have the derivative defined as the rate of change with respect to t. But then we find that we have to introduce the unit vector u, which we've done here by parameterizing it along this line that I called c. And then up at the top of this particular screen, we found that t is actually the arc length parameter. So the rate of change with respect to t is exactly what we want. We want the rate of change in the given direction of this particular line, and that direction of that line is the unit vector u. So here's sort of a visual, graphical way of what we're talking about. So you can see we have the x, y, z axes there in black. We have this, the graph of z equals f of x, y in blue. And on the bottom of the picture, it's kind of hard to see, but there is a unit vector u that's picked right there. The unit vector is based at the point AB in the xy plane. Right, so this is, you can see on the label there that we have the axes labeled, but this is the point AB. And so when we're talking about we want the point on the graph, we're looking at the point up here. And we want the rate of change in the direction of that unit vector u. So what we were able to do in this case was form this line that is tangent to that point on the surface, and it is in the same direction as u. And so as indicated here, this directional derivative we just evaluated, it is the rate of change at that point, which means in terms of the graph, it's the slope of that line that touches the curve at that point and is in the direction indicated by vector u. So let's look at an example. So let's say we wanted to find the derivative of the function f of xy given by, let's do a simple function here, 3xy at the point 2, 1. In the direction of vector v, which is given by coordinates 1, -1. So the first thing you should recognize is that this vector is not a unit vector. In fact, it has a magnitude of square root 2. And so the first step that we'll need to do here is to find the unit vector in that same direction. And so we know that one way to get a unit vector is just to scale it by its magnitude. So in this case, 1 over square root 2 times 1, -1. And of course, if we wanted to go ahead and scale it, we would get this vector here, 1 over square root 2 and -1 over square root 2. So now we have now we can go ahead and substitute everything into our limit definition. So we want the directional derivative in terms of u of f of 2, 1. That's our point. And so this is, by definition, the limit as t goes to 0 of f of 2 plus 1 over square root 2t 1 minus 1 over square root 2t minus f of 2, 1 all over t. Right? Now we have a formula for f. F is just multiplies together 3x and y. So this is just going to be 3 times 2 plus 1 over square root 2t times 1 minus 1 over square root 2t minus 3 times 2 times 1. All again over t. All right, so we just do some algebra here, and eventually we will get that the t in the denominator will cancel. And so here, in the first one, I'm not going to worry about the 3. I'm just going to multiply everything else together. So we're going to get a 2. We're going to get a negative t over square root 2. And we're going to get a negative t squared over 2. And of course, 3 times 2 times 1 is 6. All over t. So we notice when we distribute the 3 here, we have a 3 times 2 and we have a 6. Those will cancel. And so what we're going to have left is 3t, negative 3t over square root 2 minus 3t squared over 2, all of that over t. The t's will then cancel. We have a t in every term. And so we're left with negative 3 over square root 2 minus 3t over 2. And as t goes to 0, this term will go to 0 as well. And so what we're left with is just the constant negative 3 over square root 2. Right? And so this is our directional derivative at the point 2, 1 in the direction of the vector 1, negative 1. So if we were to graph the function f being 3xy, we would find the point on the graph indicated by the point 2, 1. So it would actually be in 3 space. It would be the point 2, 1, 6, because that's the function value there. So if we'd find that point and we find the line with direction vector 1, negative 1, what this tells us is that the slope of that line is negative 3 over square root 2. Right, now this was a relatively simple function, just 3xy, and it was a relatively simple vector, 1, negative 1. But you can imagine that when the functions get more complicated, this limit calculation can become much more tedious. And that is definitely the case. And so what we're going to be doing in the next video is coming up with a way to compute this directional derivative in a way that we can avoid having to compute a limit every single time. Much like in single variable calculus, you first learn the limit definition of derivative, you play with it for a class or two, and then you figure out all these different ways to simplify those calculations using the chain rule, the product rule, the derivatives of elementary functions themselves, like the sine and cosine. And so that's our goal for the next video, is to come up with an efficient way to compute the directional derivative that doesn't really involve having to compute a limit like this.